with Poisson distribution. Okay, I'm going to start with Poisson distribution. So a Poisson distribution is also belong to the family of a discrete probability distribution. Can you all hear me, right? Okay. So we use Poisson distribution to model, the occurrence of events in a specific time period. Okay. For instance, if you want to talk about the numbers of admission of patients into an emergency department of a clinic, of course, that for in a given period, that follow Poisson distribution. What about in cellular biology, where you want to, if you really want to understand cancer development, then you need to we can study the occurrence of numbers of mutations, okay? Numbers of mutations that occur, in a given numbers of cells, okay, in a given period, okay? If we're able to understand that, of course, to be able to understand that number of occurrence of mutations in a given period of time, of course, the use of Poisson distribution can actually be used. Okay, we can use Poisson distribution for all of that. Okay, now I want to go into the mathematics of it. Okay, there's so many examples. I want to talk about the numbers of snake bites. Snake don't just bite, okay? That is a rare occurrence. Or what about the numbers of cases of a disease, So now, if X follow POI, when you see POI, that's an abbreviation for Poisson, okay? With parameter lambda, okay, you're actually going to see the way I've been doing this. Distributions are parameterized, okay? For binomial, of course, N and P. For negative binomial is R and P. Okay, right now we're dealing with a Poisson distribution. The parameter of interest is lambda. Okay, so the probability mass function, okay, is this. Okay, this is the probability mass function for Poisson distribution. Okay, now when you take a look at this, X represent the numbers of characteristics of interest, and that X is having a state space of this to infinity. So if I were you, make sure you understand state space. Every probability distribution has its own state space. Okay, now the very first thing I'm gonna do right now, okay, can we show that this is a valid PMF? Okay, how can we show that this is a valid PMF? Okay, when I say PMF, of course I mean the probability mass function. Now, if I want to show whether a particular probability distribution is a valid probability mass function, because the random variable here is discrete, then we need to show that the sum of that probability, okay, over the state space, okay, S start from 0 to infinity has to be equal to 1. Okay, the moment it is equal to 1, we're actually going to say, okay, this is a valid PMF. Now, what I'm going to do right now, I'm going to have this. Well, what is the distribution? Exponential is the power of that divided by x factorial. And right now, this is a constant. I can rewrite this guy as this. Any question? This is a constant. I put it out. Now, if I want to write this mathematically, this is like lambda raised to power 0 factorial. And by the time you do that, that's going to be 1 plus, lambda divided by 1 factorial. so which is going to be lambda squared in this case. I mean lambda in this case plus lambda raised to the power 2 divided by 2 factorial, lambda raised to the power 3 divided by, this continue to go like that. Now when you take a look at this, okay, if you've done Taylor series expansion before, this guy is the same thing as exponential raised to the power lambda. Okay, so this is the same thing as this. Okay, take a look at this guy here. Okay, mathematically speaking, this is the same thing as this. And here, what is going to happen? What is going to happen when you combine them? Okay, it's like you're going to have this. And what have you done? So you've been able to prove that Poisson distribution is a valid PMM. Let me tell you this. It is not all function that qualify to be a probability function. Before a function can be a probability function, if the random variable in that function is discrete, the sum of that probability has to be 1. Okay? When we start a continuous distribution, we're going to be talking about integral. Right now, we're talking about sum because we're dealing with a discrete random variable. Is there any question? Any question? All good, right? Now, I quickly want to go into the derivation of the mean and the variance. Okay, I want to go into the derivation of the mean and variance. So I'm going to first start with the mean of a Poisson distribution. Mean of Poisson distribution. Okay, expected value of x is lambda. So I want to prove that now. Okay, I want to start the proof. Okay, expectation of x for a discrete random variable is summation x this. Okay, the state space here 0 to infinity. That's a definition for all discrete random variable. So right now I'm actually going to have this x. What is it? What is the distribution? It's exponential raised to the power this raised to the power that divided by x factorial. Okay? Now, when I have that guy now, okay, so when I have this guy now, expected value of x, it's actually summation x start from 0 to infinity x exponential raised to the power this lambda raised to the power x over x into x minus 1 factorial. X factorial is the same thing as x into that. So this cancel that. Okay, the constant should come out. This is going to come out. I'm going to have this to infinity. Then I'm going to have this. Okay, but when you take a look at what I have right now, this is carrying ahead. This is x minus 1, and this s can start from 0 again. So I can, let me just simply write summation. Then I want this to have a power of x minus 1 so that I'll be able to apply an established mathematical rule. Now, because of that, I'm going to introduce a dummy, this and that. Okay, introducing that is going to come out. I'm actually going to have this guy. Then I'm going to have this. Okay, look at what I have right now. Okay, so I can let y to be this, right? If I let y to be that, I'm actually going to have this. Okay, lambda raised to the power y over y factorial. Y can now start from 0 to infinity. Okay, now if you take a look at this from the definition, that's an exponential raised to the power lambda. So right now I'm actually going to have this and this. Okay, so this guy cancel that guy. So finally, expected value of s is lambda. Is there any question on how I derive the mean of Poisson distribution? Is there any question? In exam, I can give you any discrete probability function and ask you to derive the mean, the variance, and even ask you to show